So uh, just a quick recap. So we were talking about walk, closed walk, open walk. And we reached up to the definition of a path.
Sir,
So, yes,
sir, I have a doubt in the definition of path.
let me start. So let me recap and then we can talk. Okay. So, so what is a path? So we said that a path is a walk where no vertices are repeated. I'll come back to your question. So, and then we were discussing about the way to uh, represent a path. And we said that a path from V3 to V1 can be written as now. There was a question last day that why do we need to mention the edges? So one, as I said, that it's important to mention the edges in presence of parallel edges. Okay, so to make the definition generic. There is another reason, because the definition of path generalizes to directed graphs also. You could have a situation like this, right? And in this case, the construction is not admissible. Okay, and therefore you need to mention the edge. Fine. So this is another reason why you need to mention the edges. Of course, like you can have a different way of describing things. Like when you write computer programs, you can have different ways of describing things. You can like describe this whole thing as tuples of vertices representing edges. One more thing that I did not tell you last day is that non-repetition of vertices puts an additional implicit constraint. Can you tell me what? After this, I'll come back to your question. Can you tell me what? This automatically puts an implicit constraint.
Non-repetition of edges as well.
Excellent. So this means if you cannot repeat vertices, this automatically corresponds to, as a corollary, non-repetition of edges. And you can verify it. Take any example and see, you will not be able to repeat an edge without repeating a vertex. Okay, this is not possible. And you can just show it through inductive arguments. Yes, now coming to the confusion. Somebody had a confusion
Yes, sir.
regarding,
Sir,
yes.
Sir, in the definition of path, you have told that a path is an open walk in which no vertices are repeated.
Yes.
Sir, since we have mentioned the term open walk, is it necessary to mention no vertices are repeated?
In walk, vertices and edges are all repeated. You have forgotten the definition of walk. In a
Yes, sir.
walk,
But in
both,
open walk,
yes. In open walk, it's all vertices and edges are repeated, only that the endpoints are not same.
okay, sir.
Sir,
Yes.
so you said it is necessary to mention the edges in directional graphs, directed
Yes.
graphs.
Yes.
But by the direction of arrow, we can see that if we write V3, V1, V2, sorry, V3, V2, V1, then there is only one directed edge even.
Yes.
So
Yes.
will that create any confusion?
Yes.
If,
Yes. Because there are two edges between V3 and V2. Which one are you referring to? Nobody knows.
but sir, from V3,
Unless you write it in this way. Which explicitly indicates that the edge is directed in this direction. So as I said, the way you are representing, your internal representation has to be consistent. So this is one way of consistently representing it. You can choose any specific way of consistently representing it. No harm in that. Circuit, not the one from Munna Bhai. So this is a closed walk where no edges are repeated. Okay. Does not mean that vertices cannot be repeated. So putting a constraint on edge repetition does not automatically put a constraint on the vertex repetition, but the opposite is true. Okay, so this is a one-sided clause. And cycle, which is something that you will see recurring in many different applications. A path that has, it's a path, okay? A path that has the same start and end vertices. Okay, this is a closed path. A graph having a cycle is called a cyclic graph. One is enough. A graph that has no cycles is called an acyclic graph. A directed graph with no cycles is called a directed acyclic graph, for short known as DAG, and this is a very important construction for many different CS applications. We will see through it. Why is it so? So this has a very special property. Directed acyclic graphs or DAGs have very special properties, and we will see how these properties can be exploited. So you'll see the special property in the theory class, and some of the applications of this property will be discussed in the tutorial, in tomorrow's tutorial. Subgraph.
So,
Yes.
in the definition of graph, we learned that it is an open path. Sorry, in the definition of path, we learned that it is an open walk. So, how do we define cycle like that? How do you define cycle as a closed path? Because path essentially says that no vertices are repeated, but in cycle, the start and end vertices are the same.
Yes, that's the only exception. So in a cycle, it's also a path, but it's a specialized path. It's a specialized path where only the start and the end vertices are repeated. All other properties of a path remains the same. So So if you're not asking questions, can you please mute yourself? Yeah, so this is a cycle. So it has the properties of the path, and it also has this thing that it's like the start and the end vertices are same. Yes.
So what did you write for DAH, directed acyclic graph?
DA, directed acyclic graph, that is a DAG.
DAH, sir, or G?
DAG, directed acyclic graph.
Okay.
Directed acyclic graph. DAG. Okay.
Sir?
Now that, yes.
Sir, you have drawn this cycle, so means we can call it as a path.
Why not? It's a special path, as I said, it's a closed path.
Means it is a path. We can call it as a specialized
Yes,
path. Okay.
yes. It's a special path. Okay, so now the chart that I was talking about. Walk, circuit, path, cycle. Vertices may repeat, edges may repeat, could be open, could be closed. Vertices may repeat, edges cannot repeat, closed. Vertices cannot repeat, edges cannot repeat, open vertices cannot repeat except start and end edges cannot repeat closed. So this table should be in front of your eyes all the time. And things become much more easy go. A subgraph. So as the name suggests, it's a sub of a graph. Okay. So what do we mean by sub of a graph? So here, say S is a subgraph of G. Then S then let's say S equals V prime E prime and G equals VE. V prime is a subset of V and E prime is a subset of E. Okay, so this is how you define a subgraph. So all the edges in S are in G and each edge in S has the same endpoint as G. Suppose this is my original graph G. So different instantiations of S could be as follows. This could be S. This is another S. This is another S, and so on and so forth. So there is a
Sir, if
spatial.
it is present, then it is not necessary that the edges between them should also be present in S.
Huh?
If two vertices are present in S, then is it not necessary that the edges between them should also be present?
Very good point. That brings me to the next concept. So what you are telling is called an induced subgraph. So an induced subgraph is a subgraph where if the vertices are present in S and so let's say if two vertices, let us say if two vertices. If two vertices, say U comma V, U comma V are present in S and there is an edge between U and V in G, then there must be the same edge also present in S. So if I take the previous example, this is a subgraph, whereas this is an induced subgraph. Okay,
Sir,
go ahead, go ahead.
so is it possible that we have only edges but no vertices?
No, that's not possible, because then the basic definition of graph is violated, right?
Okay, sir.
Sir, I didn't get the difference between subgraph and induced subgraph.
So what is the difference between these two?
One is open and other is closed.
No. See, look at this graph.
Each vertex is joined.
Yes. So see, in this graph, if I take the subset of vertices 0, 0, 3 and 1, right? So this is a subgraph by definition.
Yes, sir.
Okay. Now what is the difference? Here, as many edges as are there among the 3 vertices in the original graph, those many edges should be retained here also. That is the additional constraint.
Okay.
Got it?
Yes,
Everyone got it?
Yes, sir.
Yeah. Okay. So for instance, if I have all the 4 vertices, then this is an example subgraph. But if I have to have an induced subgraph in this case, then what will it be? If I have to have all the 4 vertices?
Same as G.
Yeah, it should be the same graph.
Also, sir, the edge can only be there if the endpoints are there in the S.
Absolutely. Yes. The last in line, connected graph. So a graph G is said to be connected if there is at least one path between every pair of vertices. So in the first graph, there is a path existing between in every pair of vertices. In the second graph, This is a disconnected node from the rest of the network. Okay.
Sir,
Yes.
every pair means we choose any two vertices. There must be an edge between them.
Yes.
Like this.
Not
Then-
edge, not edge, a path. Not edge.
Okay.
Okay. If you choose every pair of vertices and there is an edge between them, then that's a complete graph.
Yes.
Okay. So now we are more or less done with all the definitions that we need. There are many other definitions. So graph theory is a huge syllabus in itself. Okay, so like we are just using those definitions which are like very much needed for our algorithmic purposes. I mean algorithm design purposes. So now we'll talk a little bit about computer representation. How do you represent a graph in a computer? Okay, so there are two different ways of doing this. One is called an adjacency matrix. The other is called an adjacency list. So as the name suggests, the first one, adjacency matrix, okay, it's a matrix representation. Of the graph. Let us say we again have GV as the graph and there are n nodes in the graph, okay, and n is mandatorily larger than or equal to 1. So G is typically represented as a 2D array. Okay, array or matrix, whatever. Such that each entry Aij is equal to 1 if and only if the corresponding nodes Vi, Vj in the graph is an edge. Okay. So suppose best is to represent things pictorially. Say you have a graph like this, then your adjacency matrix is as follows. So anywhere there is an edge between two nodes, the entry is 1, else the entry is 0. Okay.
Sir, A, D, D, shouldn't it be 0?
A,
D,
B,
D.
A, B, D. These are pairwise things. How,
Sir,
what do
4,
you,
comma 4 is what I'm talking about.
Yes, sir. 4, 4 is 0.
ED,
DD.
No,
DD?
sir. It has self
No,
DD,
loop.
sir.
it's,
Yes.
no, it's, there is a
Self.
self loop.
Okay, sir. So this is a path. One represents a
Okay,
path.
okay. Yes, sir. Yes, sir.
This
Got
is
it.
a self loop. This is a self loop.
Yes, sir. I did see that. Yes, sir.
Okay, okay, sir.
So otherwise it is 0. If there is no self loop, then it is 0. So if there is a self loop, there will be 1 here. Okay. So now quickly tell me, if I sum the row entries for A, what do I get?
The degree of
Degree of
A.
A.
The degree of A. Very good. Yeah. So this is something that you can remember always. So if you sum the elements row wise in this matrix, you get the degree of the corresponding node. For the directed graph, it's same. Only the direction is maintained. So if Vi, Vj is in E, then there is an entry Aij equals to 1, and if Vj Vi is also in E, then a Ji is also 1. Okay. So here these two becomes distinctive. Okay. So this matrix, anything different between this matrix and the matrix that will be formed by the directed graph?
So the previous matrix is symmetric and this may not be
Yeah,
symmetric.
this is symmetric. This is symmetric. Okay. And this is
Need not be symmetric.
depends.
Sir,
May
then
not be
for
so.
graphs with multiple edges, do we write 2 or the number of edges, or just is another way of representing?
No, so since we mostly have like, um, this is a nice question. Since we mostly deal with simple graphs, we typically don't care about representing multi edges. But what one can do in such cases, when you have multi edges, okay, there are different ways of approximating it. Approximating a multi-edge could be, you can imagine, okay, there are 2 edges, so let me maybe have weights on them and call it a weighted edge of weight 2. Okay, there could be multiple ways of approximating it. It's not so easy to represent a multi-edge, okay, in for our like computer representation. So this is one way of representing it. There could be many different other ways that one can think of, tricky ways. For instance, you can have something like say 1 1. I mean, so some sort of an internal notation. So basically, this follows naturally. The other one, it depends on you. It depends on the design engineer. Adjacency list. So now we will see the application of a list. So this is one of the beautiful applications of a list in representing a graph. So in this representation, every vertex of the graph contains a list of its adjacent vertices. So if there are n nodes, then there will be n such lists. In this set of lists, I represents, say, list number I represents the nodes adjacent to node I. So for the example that I have shown here,
Sir, is there any order in, to maintain while writing this?
I could
Is
not
there-
get you.
Yes, sir. Is there any order to maintain? Like for the list starting with 0, can we write 3, 2, 1? Or it shall be only 1, 2, 3?
No, anything is possible as long as the adjacency list is maintained. Like you have to represent all the edges basically that are adjacent to 0. Any order is fine. You can also represent directed graphs. So you can represent both undirected and directed graphs using both adjacency matrices and adjacency lists. Now tell me, do you see any advantage of adjacency lists over adjacency matrices?
The input size is less.
Input size is less. Where is the input size eaten up in the adjacency matrices?
Where there are no edges,
When there
V
is no
equals to
connection, we are
0.
not
When there are,
reducing.
yeah, so basically, so remember, if it is a sparse graph meaning less number of edges, you always prefer adjacency list. However, if it is a dense graph, like a complete graph, say, okay, both give similar benefits.
Sir,
Hmm.
so just by looking at an adjacency list, can I tell whether it is directed or undirected?
Just by looking at an adjacency list, yes, why not?
How, sir? Like this can represent both undirected graph and directed graph. If it is undirected graph, it only means that this is mapped to this and this is also connected to that.
Yeah. So what you can do is you can put a direction pointer. You can keep a direction pointer.
Excuse me,
Hello.
yes, sir. If there is a particular list, then does it follow a particular path? The nodes of the list. That there is a 102. So I
No,
don't
I
see a
don't
path.
get you. I don't get you.
Sir, I want to ask that if there is a particular list, so and nodes of that list follow a particular path,
No, 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 no.
connected node.
This is just the representation of the graph. You have to construct the path from the graph.
Okay, sir.
Okay, this is just the representation. This is just the computer representation. So these are ADTs basically. So this one is a matrix, I mean a 2D graph, and the other one is an ADT to represent the graph. From here you have to compute everything, paths, etc. Everything needs to be computed. And we need to learn algorithms for doing all of those. So the first and the foremost type of algorithms that we will learn, and then this saga will continue, like in tomorrow's lecture, later on when you will learn about shortest paths on weighted directed graphs and things like that. So these graph algorithms will keep continuing. Okay, so the first algorithms that we will learn about is traversal on graphs.
Sir,
Go ahead.
sir, while representing the directed and undirected graphs, if a graph has in a directed graph we have direction in, I mean path or edge in both the directions.
Yes.
Then how can we differentiate the undirected and directed graph?
So undirected and directed graph.
Yes.
So yeah, so basically as we have done it here, in this particular case itself, there is a reciprocal edge, right?
Yes, sir.
You can use doubly linked list also, but singly linked list is enough. So here it shows that there is a directed edge between 0 and 1, and there is also a directed edge between 1 and 0.
Yes, sir.
Right.
And also, if we represent the undirected graph of this, it will be same as the directed one, right?
No, if it is an undirected graph, then this means a parallel edge, right? This becomes a parallel edge. We don't really know how we will represent that.
No, sir,
Like
we don't.
if it is a parallel edge, or if it is a single edge. If it is a single edge, yes, the representation is same. Only
Yes.
for a directed graph, you can have a separate bit indicating that this is a directed graph.
So can you repeat this?
So for a directed graph, you can have a separate bit which indicates that this is a directed graph. So you know how to traverse.
But in linked list, we cannot put such thing. No, sir.
Why?
Or we take a character to
You take some flag.
Okay, sir.
You take some flag. See, so this is just facilitating a representation. Internally, you will have to use it in the context of a directed graph as it should be used, and in the context of an undirected graph as it should be used. Okay, so this is just a representation facilitation. You have to internally use it as it should be actually used in case of a directed graph, and as it should be used in case of an undirected graph for the adjacency list. For the adjacency matrix, it's much easier because you have the this additional spaces. Since you are compromising these additional spaces in the adjacency list, so you have to maintain some additional bit information or something additionally to indicate that this is a directed graph. Okay, so we will talk about two types of traversals on graphs. The first one is called the depth first search. And the other one, the other side of the coin, is the breadth first search. So as the name suggests, you are in search of the vertices somehow. So one goes depth by depth, the other goes breadth by breadth. What does it mean? So suppose we have a graph like this. We will start with DFS or the depth first traversal. So this is in short called the DFS, and this is in short called the BFS. So a DFS, as I said, traverses depth by depth. So you say you start from 1, not necessarily that you have to start from 1. Say you start from any arbitrary vertex. In this case, let's choose 1 without any loss of generality. So we start from 1, then it moves depth by depth. Goes to 2, goes to 3. So here it is an end of depth. Comes back to 2, goes to 4. Here again it is an end of depth. Comes back to 2, comes back to 1, goes to 5, goes to 7, goes to 6. It could have gone to 6 and then 7. Okay. So goes to any one of these is possible. Goes to 7, goes to 6, come back to 7, come back to 5, and then come back to 1. Okay. So this is a depth by depth traversal. And as you see that there are arbitrations at different points, right? And therefore, there is not a single DFS traversal. A graph can have multiple DFS traversals. And as long as we get one of them, we are happy. Wherever we have to arbitrate, we arbitrate randomly. But as long as we get one of them, we are happy. So how do we write a pseudocode for this?
Sir, I didn't understand what I've done there. Like after we get to 4, then we can go to 1 also.
Yes, but you have come from 2 to 4, right? So you have to get back to 2 and then you can get back to 1. So 4 is discovered as a neighbor of 2, not of 1.
But sir, it is a neighbor of 1 also.
Yes, but you are traversing. So it's a traversal, right? So you have come to 2 and from there you have gone to 3. You have come to 2. You are now checking if there are anything that is left of 2. Any other neighbor of 2 that is left. Okay. You see 4 is left. You visit 4. You get back to 2. Now you get back to 1. And then you see if anything else of 1 is left to be visited. You don't find anything. That course is what I am showing. Or you could have gone in a different way. You could have started with 1, you could have gone to 4, and then you could have explored 2 and then 3. That is also possible. That's what I'm telling. That you could have multiple ways of doing the traversal.
But
Yes.
sir, how will we know on beforehand? Like when we go
We
to
don't-
4,
We don't know. We don't know, right? So it's arbitrary. We don't know. So that's why you can have multiple DFS traversals on a graph. And as I said, as long as we get one of them, we are happy. Okay? As long as we get one
So
of
we are
them, we are.
talking about efficiency. Like to get to 4, we have to go from 2 and then to 4.
Huh? Come again?
If we have to go from 1 to 4, then from the first traversal, we will first go to 2 and then to
Yes.
4.
Yes. Yes. True.
So this is inefficient, na, sir.
Why?
So we can directly go to 4 from 1.
No, then you have to come to 4 somehow again. You have to visit all the vertices. From 2 to 4, you have to come, right?
Yes.
So that the cost is effectively same. In this way, you have also told me what is the cost. What is the cost?
When, sir?
You have to traverse all the nodes and all the edges.
Sir, 2n.
No, why 2n? There, as I said, these graph data structures have two input sizes. Say m, number of edges, and n, number of nodes. So then, what is the cost of the traversal?
N plus m.
No matter whatever you do, this should be the cost. Now, question is, how do we write an algorithm for this?
sir, I was asking when we come to 4 from 2, then if there is another neighbor of 4, like some 8, then we will go to 8 and come back to 4, right?
You will go to 8, come back to 4.
But if 8 is not there, we will search for the neighbors of 4 and we find 1 is there. So why won't we go to 1?
That's the thing. So now how do you stop that?
Sir, what if 8 is connected to 3?
I do not want to revisit something that I have visited. I do not want to revisit.
I'll hold an array of already seen nodes.
Array? Will you hold it in an array? Yeah, somebody asked something else. So can you repeat your?
So what if 8 is connected to 3?
8 is connected to 3. So what?
So shall I go back to 4? Like
No. You will then explore first 3 because 8 has a neighbor. You want to explore everything of. So you are going depth by depth, as I said. Once you have come to a depth, you have to explore the depth further.
So while returning, then I will go back. While returning, I will go to 3 to 8 to 4 to.
You will go to 3 to 8 to 4 to 2 and then to 1. How do you simulate this? Start from 1, come to 2, 4 or 3, whatever. 3 done, go back to 2, come to 4, 4 done, go back to 2, then 2 done, go back to 4. Every time I come somewhere, I mark it as visited and I do not want to visit it anymore.
Sir?
Or I should have some control on visiting it. Yes.
Sir, if I've already visited 3 from 2, why will I go from 8 to 3 again?
Depends on which way you are progressing. You could go to, so see, 2's neighbors are 3 and 4. Okay. So somebody asked that if you come from 4's route, what will happen? You can also come from 2's route and explore in this way because this is a cycle.
Yes, I got it.
So how do you simulate this? How do you prohibit that if something is there, then I should go down and not go back? And once everything below me is explored, I should go back.
So we can use a flag
Find the
in
null
every node.
factors.
We should
Somebody,
use a flag.
Find the
somebody,
null.
yeah, come again. One of you said
We have to
something.
find. We have when we encounter a null, we have to go back.
No, somebody else said something. We have to use a special data structure here.
We have to attach a flag to every node.
No. You are not looking at the traversal. Stack. Excellent. So how is the stack helpful?
Sir, every node.
So
we
once visited,
traverse,
we
we
can
put
pop
on the
out the.
stack. And
Once
once we
visited, will you pop out?
No, once visited, we
Once all
add
its
stack.
depth, once all its depth has been completed and you come back to it, you pop out.
Yes, sir.
So the algorithm is as simple as processing a stack. I'll write the algorithm today and tomorrow we will discuss. Say we are starting from node U. We say that we set U as visited. Now we look at for every outgoing edge, UV do if V is not still visited, then so for this above graph that I have drawn, let me draw it once more here. Try to find out some of the DFSs, possible DFSs. Maybe for the time being, start from 1. So do this homework.
So can you please upload these slides?
Yes, I will. Yes, I will. Next day we will discuss the algorithm in details. Okay, we'll stop here and I'll upload these slides. Huh?
Can you scroll up a bit?
Can you show sir once?
So inside the if condition, u dot visited equal to false, you should mark it as true, right, before calling the FS visit.
Huh? This is v dot visited equals false.
Yes, sir, yes, sir. So we should mark it as true, right, before calling the FS visit.
Why? As soon as you call DFS, this is a recursive function.
Oh, okay, sir.
So you understand how the stack is implemented here. We are not using any stack at all. We are simulating stack using
recursion.
yes. Because recursion is known to be running on a stack. Okay, you implement recursive calls through a stack. So therefore, we don't need to have any stack additionally implemented. You can just use a simple recursive call to simulate the stack. Try to understand this algorithm with some example graphs. Okay, and next day, tomorrow, we will see like one or two of these visits and we will learn a few more things.